All right, so let's begin chapter 3. There's only a few sections in this chapter, so we should be able to get through chapter 3 fairly quickly. So we are going to be talking about systems of linear equations in two variables in this chapter. We'll also eventually talk about systems of linear equations in three variables. Basically we'll have, multiple unknowns, and we'll be able to use some techniques that we're going to learn to be able to solve for both of the unknowns. At this point, we're able to solve equations with just one unknown in our equation. And we're going to extend that to multiple equations with multiple unknowns in this chapter. Okay, so essentially we have this linear equation here, which is fishing. We know that it has a negative slope. This is the hiking equation as well, the line that represents the equation. And you can see here that there is a point of intersection. Now it's sort of like floating in space here. It doesn't look like it's exactly at, in the middle between 8 and 10. Looks sort of like, maybe 8 and 3/4 or something like that. Which is why just graphing these equations to find where the intersection is not always super useful, because sometimes the intersection kind of floats in space there, and you either need to make an estimation of where it is, or you can actually use some other techniques that don't even use the graph at all to be able to find out exactly where that intersection point is. All right. So we are going to decide whether the given ordered pair is a solution to the given system. So here's our ordered pair over here. And basically what we want to do is we want to make sure that this point satisfies both of these equations. If it satisfies both of them, it is called the solution to that system. If it only satisfies one and not the other, it means it's a point on that line, but it's not a point on the other line. So we're going to go ahead and check it to see if this is in fact a valid solution. So let's do 2 times -4 plus 2 is equal to -6. So again, I'm just substituting -4 and 2 in for x and y over here. And that's going to give us -8 plus 2 is equal to -6. And -6 is equal to -6. So this checks out. So far, so good. It is a point on this line, so we're going to check to make sure that it's a point on this line as well. So -4 plus 3 times 2 is equal to 2. -4 plus 6 is equal to 2. And 2 is equal to 2, so it checks out for this one as well. So this is the ordered solution to the given system. And usually when you're talking about systems, you oftentimes have these curly brackets here that will represent these two equations are linked together somehow. Okay, so we'll do the same thing here just to check to see if this is also a solution. So to this other system. So we've got 2 times 3 plus -12 is equal to -6. So this is going to be 6 minus 12 is equal to -6, and definitely -6 is equal to -6. So far, so good. So this is definitely a point on this line. Now we have to check to see if it is a point on that one. So we've got 3 plus 3 times -12 is equal to 2. And you've got 3 minus 36 2. And there is no way that that's going to be even remotely close. So again, this was a solution to the first equation. It was not a solution to the second. So this is not a solution. Okay. So now we're going to solve this system by graphing. And what I'll do is I'll see if I can change the colors to correspond with the color of the equation here. So we'll start with blue. So we're going to graph this equation here, and I'm going to do that by converting it into slope-intercept form. So this is going to be y is equal to -2x minus 5, again, subtracting 2x to both sides. So if it's in slope-intercept form, I start with the intercept, and then I use my slope, which is down 2 to the right 1, but of course I can't do that because I would go off the grid. So I'm going to go up 2 and to the left 1, still representing my negative slope. It's still going down from left to right. And I'm just going to put in a couple of additional points in here as well, because again, I'm going to be looking for a point of intersection. So the more points that I have, the more accurate my picture is going to be. So I just continued my rate of change, that slope, so that way I have all of these points here being represented. Okay, so now I'll go to the red one and just go back to red. And this one I'm going to, as a variety is the spice of life, right? So I'm gonna put this one and I'm gonna use my intercept table, okay? I, of course, could, if I wanted to, convert it into slope-intercept form. Again, it doesn't matter how you graph these. These graphs are going to be the same. It's just I'm choosing to use the intercept table for this one for no particular reason, except for the fact that variety is nice. So we've got a 0 that we're going to substitute for x, which means we're going to solve for y. And we divide both sides by 3 to get a 2 there. So we have one of our points that is going to be 0, 2. So there is one of the points right there. And then the other one, I'm going to substitute 0 in for y to figure out what x is. And this is going to be -6. So it turns out that this became problematic for us because we are now officially off the grid here. Our grid only goes to -5, which is pretty small. So it was kind of a bad idea to use the intercept table, and only because my grid is so small. Usually the grids go from like -10 to 10, so it's very rare that you would have an issue. But I'm having an issue here because, again, my grid only goes to -5. So I'm going to switch gears a little bit and convert this into slope-intercept form. So that'll be y is equal to, this will be 1/3 x plus 2. So there is my my conversion into slope-intercept. Again, I added x to both sides and then divided everything by 3, and that's where my new equation came into play. So from this intercept, go up 1 to the right 3, and I might as well do the same thing in the other direction. Go down 1 to the left 3, and boom, we can now see exactly where our point of intersection is. It's right here at -3, 1. That's where both of these points, the blue line and the red line, intersect each other, okay? So we have a few cases that we deal with when we're solving linear equations in 2 variables. Case number 1 is that the 2 graphs intersect at a single point. So if they intersect, which they did in the one that we just graphed, the intersection is going to be a single point, okay? Again, meaning that these guys have different slopes. We know that because if they had the same slope, they would be parallel to one another, and this would obviously have no solution. If we're looking for the point of intersection and the parallel lines we know by definition don't intersect, then we're never going to find that point of intersection because they don't intersect. So this would be no solution. And over here, every once in a while you graph a line and then you graph another line right on top of it. That represents infinitely many solutions here. Infinite number of solutions. Again, it's like you had this blue line here, and then you graphed another equation, and you ended up with the exact same line that you had at first, which means where are these guys touching? Well, they're always touching. Doesn't mean that every single point in the world in this Cartesian plane is a solution. It means that every single point on these lines is going to be a solution. So you're going to get infinitely many solutions with that one. All right, so it can be difficult to read exact coordinates, especially if they are not integers. So that's what I mentioned earlier with the original graph. It was kind of this guy right here. Again, it's not an integer solution here. It's sort of floating in space. So it's hard to know exactly where those intersect. So we come up with these other methods to solve these systems, and one of them is called substitution, okay? So we're going to use a substitution method, and it is exactly what it sounds like. We are going to substitute to be able to get rid of one of our variables, okay? So here we go. When to use substitution? When to use substitution is kind of important here, so I'm just going to take a minute to just kind of like give you an idea. Obviously, they're telling us to solve this by substitution, But if you're looking for the path of least resistance when you're solving these systems of equations, whenever you have a variable isolated in at least one equation, you should use substitution. So we have that here. We have a variable, this x. Doesn't matter whether it's x or y, as long as you have a variable isolated in at least one of the equations, we can use substitution. Okay, so this x is the variable that is isolated. So what we do is we say that x is equal to this. Well, if x is equal to this 2 minus y, so x is equal to this 2 minus y here, it's also going to be equal to that 2 minus y in the other equation, okay? So I call this the box and ship method when you're using this substitution, is you box up all the elements that x is equal to, this 2 minus y, and you ship it over to the other equation. So you end up with this brand new equation here, which is going to be 5 parentheses. Again, I'm taking the x out and I'm putting this 2 minus y in. 2 minus y minus the 3y that already lived there is equal to the negative 6 that was already there. So again, this is equation number 1 with the right-hand side of equation number 2 substituted into it. And this is beautiful for us because we went from having 2 equations with 2 unknowns to having a single equation with a single unknown. Yeah, this y ends up being in a couple of different places, but that's okay. We're going to be able to solve for that. This is right back to chapter 1 material here. So we've got 10 minus 5y minus 3y is equal to negative 6. 10 minus 8y is equal to negative 6. Subtract 10 to both sides, you get negative 8y is equal to negative 16. Y is equal to 2. So now that you know that y is equal to 2, we are going to be able to take this value for y and substitute it again to figure out what x is. And beautifully, in equation number 2, x is already by itself. All we have to do is substitute this value into the right-hand side. So we get x is equal to 2 minus 2, which is, of course, 0. So these are the components of your solution. The solution to the system of equations is a point of intersection. So you must write this as a point of intersection to be able to get your full credit. If you write your answer in my math lab saying x is equal to 0, y is equal to 2, they're going to take points off or they're going to mark it wrong, okay? Even though you have the right values, because the solution to these systems is a point of intersection, which has to be written as a point. Your parentheses, your comma in the middle, x component, comma, y component, ordered pair. All right, so again, we're going to solve this system by substitution. And so I'm going to go back to that, like, when do we do that? We use substitution when you have a variable by itself in at least one of the equations. And you look at both of these equations, 4x plus y equals 5, 2x minus 3y equals 13. You do not have a variable by itself, but you can get this y right here by itself very easily without even having any fractions because it has a coefficient of 1. All right, the number out front here is 1. So all I have to do to get y by itself is subtract 4x. So I'm going to create this third equation here, and it's going to be y is equal to 5 minus 4x, because again, I'm subtracting 4x to both sides. So this, again, created the third equation. It's just a manipulation of equation number 1. And now we have the variable by itself. So I'm going to box and ship over to the other equation. So that will give us 2x minus 3 parentheses 5 minus 4x is equal to 13. And now we're right back to chapter 1. Yes, x is in a couple of different spots, but we can still solve for it pretty easily. So 2x minus 15 plus 12x is equal to 13. We get that by distributing our negative 3 into both the 5 and the negative 4x. 14x minus 15 is equal to 13. 14x is equal to 28. X is equal to 2. Okay? And once we have this value for x, we'll just substitute it back in over here to figure out what y is. So y is equal to 5 minus 4 times 2, which means y is equal to negative 3. And these, again, are the components to our solution. These are the components. That's your x component. This is the y component. And your solution is 2 comma negative 3. And now you are done with solving the system. Okay, so substitution is pretty neat. The when you do it, obviously you do it when they tell you to do it. But if you're just looking to solve a system with the path of least resistance, anytime you have a variable that's by itself or very easily manipulated to get by itself, substitution tends to be a little bit easier to do. Or you can use elimination, and that's going to be the other strategy that I'm going to show you very soon. Okay. So this one is looks like it's a lot more complicated because, again, you have these fractions here. So the first thing that you really should be thinking about doing is getting rid of these fractions. So I'm going to do that by multiplying by the LCD. So if I multiply by the LCD, that's going to give me, again, the LCD is 4. I should probably throw that out there. And that will give me 2x plus y is equal to 2. Again, multiplying everything here by 4. And now we have an equation where y is pretty darn close to being alone. All I have to do is subtract 2x to both sides. So you end up with y is equal to 2 minus 2x. And then from here, we box up all the stuff that y is equal to, and we send it over to the other equation. So we end up with negative 2x plus the 5 that lives there. We are taking y out, and we are placing this 2 minus 2x in there is equal to 22. So we have negative 2x plus 10 minus 10x is equal to 22. Negative 12 plus 10 is equal to negative 12x, sorry, is equal to 22. Negative 12x is equal to 12. X is equal to negative 1. And once we have this value here, we can substitute it in. So y is equal to 2 minus 2 times negative 1. And that will be y is equal to 4. And we have everything that we need to write our solution now. It is going to be negative 1 comma 4. Okay. So again, I'm going through these pretty quickly, knowing that you can pause, rewind, go back, review. So if the speed is kind of like hurting you a little bit, just pause it, go back, and just don't try to write the notes maybe the first time you're viewing it. Just try to take it for what it is, and then you can go back and try to review the notes, or like wait for it to be completely done, take all the notes that's on the slide, and then you can go back and review it again if things didn't quite make sense the first time, okay? So taking the notes as we go along is probably not the best choice. You certainly can do that if you're a fast writer, but you're trying to write and try to digest the material that's happening at the same time, and that's a difficult thing to do. So what I would suggest is wait till it's all done, take your notes, kind of listen, take it in, and then take your notes after the fact. And if you need more review, go ahead and review it. Or if you need to ask the questions during our Q&A sessions on Mondays and Wednesdays, go ahead and do that as well. All right, so solving a linear equation by elimination. So another algebraic method is the elimination method. It involves combining the two equations in a system so that one variable is eliminated, hence the name elimination. This is done by using the following logic. If A is equal to B and C is equal to D, then A plus C is equal to B plus D, okay? So that is exactly what we're gonna be using to our advantage here, okay? So when do we wanna use elimination? So I'll start with that. So the when to use elimination. So you want both equations in standard form. which we have. So ax plus by equals c, ax plus by equals c. So we want both equations in standard form, and we want opposite coefficients on the same variable. Okay, so we want opposite coefficients on the same variable. So we have exactly what we need to be able to solve this system using elimination. Okay, so this has the negative 2x and this has positive 2x. So this is our opposite coefficients that this part says. Opposite coefficients of the same variable. So negative 2x, positive 2x. Same variable, opposite coefficients. And they're both in standard form. So if we have that, we're going to use this logic right here that says we are able to add them together. So we're going to add these equations together, and that's going to eliminate the x's, because negative 2x plus 2x eliminates the x's. And that leaves you with 5y is equal to negative 5, and y is equal to negative 1. So we were able to get our first component very, very quickly, all right, using this elimination method, because it just eliminates one of the variables very, very quickly, and then you can solve for the remaining variable that's left. And now that we know what this value for y is, we're going to substitute it back in to figure out what the value for x is. So you just pick an equation. I'm going to just highlight this one. There's no negatives in it. I feel like my life will be a little bit easier if I do that. So 2x plus 2 times the value that we just got for y is equal to 5. So 2x minus 2 is equal to 5. 2x is equal to 7. X is equal to 7 halves. So there is the component for x. And now our final answer here is going to be 7 halves, comma negative 1, and we are good to go. Okay, so elimination is pretty nice, especially when your equations are in standard form. You can manipulate them as much as possible, so long as you can get the coefficients to be opposites to one another. Things will go pretty smooth. Okay, so here are your steps for solving elimination. I'm not going to read every single one of these. You can obviously pause this video and read them for yourself, so that way you're prepared to see what is about to happen in the next slide. All right. So, do we have what we want in order to eliminate? Well, this equation is in standard form. This equation is in standard form. So far, so good. It looks promising. The problem is we don't have opposite coefficients, okay? We don't have opposite coefficients here, and we don't have opposite coefficients here. But what we do have is the multiplicative property of equality, which means we can multiply these equations by any number we want, so long as we do it to everything on both sides, okay? So what I'm going to do now is I'm going to pick a variable, and I'm going to pick x here, and I'll tell you why in a second. So I'm going to pick x, and I'm going to locate the coefficients between 2 and 3 of my x's, right? And then I'm going to think, what is my LCM between those coefficients? LCM being least common multiple between 2 and 3. And the least common multiple is 6. So my goal is to turn both of these coefficients into a 6, and more specifically, one into a 6 and the other one into a negative 6. Because remember, we want them to be opposites to one another, so that way we can add the equations. They don't have to be opposites. They can be the same. You would just end up subtracting the equations together instead of adding. So I would advise adding the equations is a lot easier than subtracting them. Less margin for error. So just stick with the opposite coefficients so you can add the equation up, okay? And again, the reason why I selected the x instead of selecting the y is that the LCM between 3 and negative 7 is just a bigger number. So that's the reason why I selected x, is that the LCM is 6 instead of 21, okay? So what I'm gonna do is I'm gonna multiply everything in this equation by 3, because that is the number that I need to multiply 2 by to get my LCM. All right, so I'm gonna get these new equations. That's gonna be 6x plus 9y is equal to 57. 3 times 19, 57. In this equation, I'm going to multiply everything by -2. Because again, if I multiply by -2, that gives me the opposite coefficient that I'm looking for. This is going to be 14y, and this is going to be 12. And now I can add these equations together. These eliminate, the x's are gone. This becomes 23y is equal to, and this is going to be 69. And when I divide both sides by 2, I get a y value that is equal to 3. And now I've figured out what one of my components is. I'm just going to substitute it into the other equation. Doesn't matter which one. I'm going to just pick the first one, and then I'll figure out what x is. So 2x plus 3 times 3 is equal to 19. So 2x is, I'll skip that step yet, sorry, is equal to 19. 2x is equal to 10. X is equal to 5. And there is our solution, 5, 3. Okay? Let's continue. So let's take a look at this one. Again, we're in standard form. Everything's good there. We don't have matching coefficients yet, but I am going to be able to get my matching coefficients. If I just multiply this equation by 4, if I multiply this equation by 4, I'll get +4 as the coefficient of y, and that is the opposite of -4 over there. You could pick the x again. It doesn't matter which one you do. It's okay. So that's going to give you 8x plus 4y is equal to 24. And hopefully you see what's about to happen here. When we add these, gone. When you add these, gone. When you add these, gone. This is the exact same line. They look different to our eyes, but they're the exact same line. So this is going to be infinitely many solutions here. Okay. So let's take a look at this one. So over here, I'm going to pick one of my variables. I'll pick x. Again, it doesn't matter which one. It doesn't change anything. I'm going to multiply this by -2, and that's going to give me -8x plus 6y is equal to -16. And this time, when you add these together, this goes away, which gives you 0 on the left-hand side. And the issue is on the right-hand side, you don't also get 0, you get -2. And the last time this happened in chapter 1, when we were solving an equation and the variables disappeared and we were left with a false statement, like 0 is equal to -2 is a false statement. This led to the empty set, no solution, okay? So the same thing is true here. When you're solving these inconsistent systems, you're going to get a 0 on one side and some other number on the other side, and that's going to lead to obviously a false situation. 0 is equal to 0 and nothing else. All right, so special cases of linear systems. Here are your cases. Again, read through these. I don't really feel the need to read them since you have the ability to pause them, this video, read them, and then we will talk about them in the next slide. Okay. So let's take a look at using slope-intercept form to determine the number of solutions. Okay, so if we get the same slope, two things could happen. They're either going to be parallel, because we know that parallel lines have the same slope, or there's going to be infinitely many solutions because we'll have the same line. So if we have the same slope in the same B, we are going to get infinitely many solutions. If we have the same slope in different y-intercepts, then we're going to have no solution because the lines will be parallel, okay? So let's convert this into slope-intercept form. So this is negative 6y is equal to negative 3x plus 9. Divide by negative 6, you get y is equal to 1/2 x minus, let's see here, 3 over 2. Okay. Again, simplifying the fraction, when you divide 9 by negative 6, you get negative 3 over 2. So there is our slope and our y-intercept for this first equation. So let's see if we can do this something similar here. So again, start to get y by itself. Y equals mx plus b. That's what we're looking for. So negative 2y is equal to negative 1x plus 3, and divide by negative 2. And that's going to give you y is equal to, again, we're going to do that to everything. Negative 2, negative 2, negative 2. Gives you 1/2 x minus 3 over 2. So we have the exact same equation twice, which means we're going to get infinitely many solutions. All right, so let's talk very briefly about the systems of linear equations in 3 variables. I'm not going to hit you guys too hard in this section. I'll take it easy on you because these are really, really tedious. It can take a really long time to do. So I'll probably only give you like maybe one question on the test for chapter 3. We'll eventually get there. Okay. So a solution to an equation in 3 variables, such as 2x plus 3y minus z, so we're bringing in the third dimension here, 3-dimensional space, is equal to 4, is called an ordered triple. Just like before we had an ordered pair because we had 2. Well, now we have 3, so we call it an ordered triple, x, y, z, and it's still in alphabetical order, so no stress there. Okay. The graph of a linear equation in 3 variables is a plane, not a line. So it is, again, going to represent a whole space, not just a thin line here. All right. The number of possible solutions are shown in the next slide, and there are many of them. All right. We are going to focus on just one of them, and I'll show you which one that is in a second. Okay. So we are going to focus on this one, where we actually get a single solution, where the intersection of these planes is a point. So think about what this actually is. If you are looking at your wall in your room that you're in right now, you have 2 walls that intersect. And when those 2 walls intersect, they create a line. There's that line of intersection, that seam that you're staring at right now. And then if you look up to where it hits the ceiling, so think of this plane, this third plane over here as the ceiling, you can see that the 2 walls that you're staring at and the ceiling intersect at that point. You could put your finger right on it. There's that corner of the room. And that is what we are going to focus on in this course. You can also see that all 3 lines can intersect, all 3 planes can intersect to create a line. You can have 2 of the planes be the same and the third one be different. That still creates a line. You have all of the planes that are exactly the same. You have 3 planes that are parallel. So think of like the floors of a building. You have your first floor, second floor, and third floor. There's obviously no intersection between those floors. Over here, you have a first floor and a second floor, and then the wall that connects all the way up to the second floor. All right, so that's kind of what's going on here. Here's your house of cards going on where they have no points in common at all. And again, there are no points in common where 2 of the planes are the same and the third one is parallel. So we, again, will focus on this first situation here. Okay. So again, I'm going to focus on case 1. All right, so here are our steps. Is we want to select a variable in the equation. It's called the focus variable. I call it the pivot variable. It's pretty much the same thing. You will use that variable to eliminate a variable in the 2 other equations, okay? So again, we'll kind of cross that bridge in a second. So we're going to eliminate the focus variable. So whatever variable you choose as your focus variable, you're going to eliminate that first in both of the other equations. And then we'll, again, this is where both of the other equations, And then we're going to write the equations in two variables that results from step 2 and step 3 as a system. So in getting rid of our focus variable, we're creating two new equations with two unknowns. And we're going to use the technique that we learned in the first section of this chapter to be able to eliminate one of those variables, and we'll finally be able to solve for one of them, and then we work our way back to figure out what the remaining values are. Okay, so let's go ahead and bang this out. So I am going to select my pivot variable. What you want to choose for a pivot variable is any of the variables that have a coefficient of 1. You can use that as your focus variable. Okay, so you have lots of options to choose from here. This has a coefficient of 1. This is a coefficient of 1. This is a coefficient of 1. So you have lots of options to be able to do this. Okay, so I'm going to select X to be my focus variable. So what I'm going to do is I'm going to use this as my focus variable in equation number 1. And I'm going to use this X to eliminate this X, and I'm going to use this X to eliminate that X down there as well. I can't do it at the same time. I'm going to kind of do it in phases, but you'll see what I'm talking about in a second. So I'm going to start by taking equation number 1 and adding it to equation number 3. And the reason why I'm going to do that is because I will immediately eliminate these X's. Because remember, my goal is to eliminate the X's in both equation number 2 and equation number 3. So I'm going to take this equation number 1, which is X plus Y plus Z is equal to 2, and I'm going to add it to equation number 3. And that will give me negative X plus 2Y minus Z is equal to 1. So when I add these up, the X's will eliminate. I have 3Y. Also, the Z's eliminate, so that's really cool for us. And that's going to be equal to 3. And I have now solved for one of my variables. Right? So very quickly, I was able to solve for Y. So I need 3 values. I already have one of them. Okay, so that's pretty sweet. I'm then going to take my pivot variable and I'm going to use it to eliminate the variable in X in equation number 2. So I am going to multiply everything in equation number 1 by negative 1, because remember, I want opposite coefficients. So that's going to give me negative X plus, you know what, I'll just leave it as minus Y minus Z is equal to negative 2. Again, I've multiplied everything in equation number 1 by negative 1 to create the opposite coefficient that I'm looking for. And then I'm going to add it to equation number 2, which has X minus Y plus 2Z is equal to 2. And when I add these up, my X's will definitely eliminate. This gives me negative 2Y plus Z is equal to 0, which is pretty sweet, believe it or not, because I have this equation here which has 2 unknowns, right? I have Y and I have Z. But earlier I found that this was my value for Y. So I can substitute that in here to now figure out what Z is. So this is going to be negative 2 times 1 plus Z is equal to 0. This is negative 2 plus Z is equal to 0. Z is going to be equal to 2. So I now have 2 out of the 3 values that I need. I can now go back to my original equation, substitute my Y, substitute my Z, and that will leave me with just one unknown X. I will then solve for it. So this is going to be X plus 1 plus 2 is equal to 2. This will be X plus 3 is equal to 2. X is equal to negative 1. And now I have all of the components that I need for my ordered triple. So this is going to be negative 1, 1, and 2. So I think that that's a good place to stop this video. Hopefully you were able to follow along with what was going on, and if you weren't, you at least marked some of these problems so that we can discuss them during our class time.